In the last video, we learned about an important kind of a series called a geometric series. We learned how to identify whether or not a series is geometric. We learned how to find whether or not a geometric series converges or diverges, and we practiced using the formula to find the sum of a convergent geometric series. In this video, we want to focus on the idea of a power series, and we're going to see a connection between power series and geometric series in one of the examples, and we'll actually see a connection back to the first example that we saw in Desmos at the very start of this section, and that will hopefully clear up some of the confusing stuff from that strange little Desmos visualization that we looked at. So what is a power series? A power series is an infinite series of this form. We have the sum of c sub n. We want to think of these c sub n's as coefficients. And then we have a variable x. If we were to expand this out, we'd start with n equals 0. So we have c sub 0 times x to the 0, which is 1. That's our first term. The next term, c sub 1 times x to the first, c sub 2 x squared. We get this expression here. This should look fairly familiar. This is actually a polynomial that just keeps going. I know the name sounds kind of strange and I mean, it sounds cool, right? Power series. But a power series really, it's just an infinite polynomial. That's a really good way to think of what a power series is. It's just a polynomial that keeps on going. And here is the form. We can generalize this form by replacing the x with an x minus a. So just imagine taking this expression here and replace the x with x minus a. If you replace x with x minus a, then you get this generalized form for a power series. This is called a power series centered at A. Right now it might seem a little bit strange to have this generalized form, and it's not really obvious what power series are useful for. We'll see one example of power series in this section, and in future sections we'll see a lot more with power series and see just how powerful they are. Power series depend on the variable x. So we have the x, which is just a variable. We can imagine taking different values and putting them into the series for x. So we could put in, say, x equals 1 or x equals 1/2, x equals 50, whatever we want. And depending on what value we place in for x, we can have either a convergent or a divergent series. So power series can converge for some values of x, but depending on the series and depending on the values of x, sometimes if we put in different values of x, the power series will diverge. And this is all dependent on whatever our example is at hand. But we have this general concept that we can put in different values for x, and we'll get a specific series here that's all in terms of numbers. Sometimes that series will converge, and then depending on our power series, other times it will diverge depending on what we input for x. In future sections, we are going to see how to represent some functions using this concept of power series. Actually, in this section, we'll see one example of this, and we'll generalize in some future sections when we talk about Taylor series. For now, let's work through example 5. Here we have the power series, which is just the sum from 0 to infinity of x to the n. Does this look familiar? If we expand this out, we're going to get that polynomial that we looked at the very first video of this section when we looked at that Desmos example. So let's go ahead and find the center of this power series. We'll expand it out and explore what happens with this power series. Let's copy down our series. The power series is the sum from 0 to infinity of x to the n. In part A, we want to find what is the center of this series. We call this center A. We want to know what is it equal to. The general form for a power series, let's just write that off to the side. The general form is the sum from 0 to infinity. We have some coefficients, which we call c sub n, x minus a to the n. In our specific example, all of these coefficients are 1. So we just have a bunch of 1s here. And then we have x minus a. Well, x minus a here is just x minus 0. So this power series is centered at 0. The a value here is 0. We can just think of this as x minus 0 raised to the n. This is a power series centered at 0. Let's write out the first several terms. This is really just expanding out sigma notation as we've done before. If we write out the first several terms, we're just going to first put in a 0 for n. So that would be x to the 0 plus x to the first plus x squared plus x cubed. I want 5 terms, so plus x to the fourth. X to the 0 is simply 1. So let's just write this as 1. And then x to the first, that's just x. And Does this look familiar again? 1 plus x squared plus x cubed plus x to the fourth. Yeah, this is what we were typing in Desmos earlier. So this goes on forever, but here are the first 5 terms for this power series centered at 0. In part C, we want to know what would happen if x is between -1 and +1. If x lies between -1 and +1, we want to know what does this power series converge to? This question might seem a little bit mysterious. How are we supposed to know whether or not this power series converges? We haven't talked about convergence of power series, so how do we know what happens here? Well, look at the form of the power series. 1 plus x squared plus x cubed. This is a power series, yes, but it's also another special kind of a series. What kind of a series is this? This is a geometric series. We have a common ratio of x between the consecutive terms. We're used to seeing r for the common ratio, so this doesn't quite look like the form that we're used to. But really, if we think about multiplying each term by x, we get to the next term. So this is actually a geometric series with a common ratio of r equals x. And now we're trying to answer the question, if x is between -1 and +1, can we determine whether or not the series converges and what it converges to? One way that we could write this expression, -1 less than x less than 1, we could express this as the absolute value of x is less than 1. These two expressions are equivalent. And this should look like absolute value of r less than 1. Our common ratio is x. And if we're assuming that the common ratio has an absolute value less than 1, then we know the series converges. So if x is less than 1 in absolute value, this would imply that our series, which we're now thinking of not just as a power series, but also as a geometric series, our geometric series will converge. We have a geometric series that converges with a common ratio of r, which is x. And if it converges, we know that the formula is the first term divided by 1 minus the ratio. The first term is just 1, and the ratio is x. So this will converge to 1 divided by 1 minus x. Are you starting to see the connection here? This is the function that we looked at in Desmos, that the polynomial was starting to look more and more like as we added more and more terms. So now the connection between this function and this infinite polynomial, this power series, should be a little bit more clear. This power series is also a geometric series with a common ratio of x, and using the sum for a convergent geometric series, as long as x is between -1 and +1, we can find that this geometric power series converges to the function 1 over 1 minus x for all of the x values between plus and minus 1. To summarize, we can actually make this astonishing conclusion. This infinite power series, the sum of x to the n from 0 to infinity, is equal to the function 1 over 1 minus x, as long as the absolute value of x is less than 1. We have an exact equality here. As we take an infinite power series, this infinite polynomial, will be precisely equal to this rational function. This is not a polynomial, yet this non-polynomial function will be equal to this infinite polynomial as long as we take x values with absolute value less than 1. For part D here, let's look at Desmos, and we'll graph the first 50 terms of this series along with the function 1 over 1 minus x. We're graphing the power series 1 plus x squared plus x cubed, etc., up to the first 50 terms. So this would be up to degree 49. And we don't want to just sit here typing that all in. Desmos can do sigma notation for us. So we can write sum, and then Desmos automatically opens up the sigma notation. I'm going to go from 0 to, I'll just call this m, and ultimately I want m to be 49. If we have m equal to 49, then we would have 50 terms because we have terms from degree 1 to 49, including a degree 0 term. So we could do m equals 49. That would give us the first 50 terms. Let's start the index here. Let's start m at 1. We'll actually look at what happens as we take more and more terms of the polynomial. And we'll go up to 49. And we'll do a step size of 1. So this is the upper limit, if you will, or the upper value here for the sigma notation. And the sigma notation, we're just adding up x to the n. So that right there, that would be the first 50 terms of this power series. If we take 1 plus x squared plus x cubed, all the way up to plus x to the 49, that's the first 50 terms. We want to compare this to the function 1 over 1 minus x, which is that function right there. And look how similar these functions are. And they're similar, except we see this behavior here. The functions are wildly different right here. They look the same between -1 and +1, which is exactly what we would expect. This power series is a geometric series with a common ratio of x, and a geometric series only converges when the absolute value of the ratio is less than 1. So we want the absolute value of x to be less than 1. That's all the x values from -1 to +1. So from -1 to +1, this power series looks very, very close to 1 over 1 minus x. But for other values of x, for x values less than -1 or greater than +1, this function does not describe the power series. The power series diverges if x is less than -1 or greater than +1. This is a very important concept. We have an infinite series, a power series, which we are using to represent a function, 1 divided by 1 minus x. And this power series only works on a certain interval. It only works on the interval from -1 to 1. Our power series, remember, is centered at 0. And we call 1 the radius of convergence here, because from -1 to +1, a radius of 1 around 0, we have a convergent power series. It converges to 1 over 1 minus x. The more terms we take for the power series, the closer and closer the power series will look like the function, as long as we're staying between -1 and +1 on the x-axis. Let's look at what will happen as we add more and more terms here to this polynomial. So if we start here with m equals 1, this is just x plus 1. And as we increase the value of m, that will give us more and more terms for this series. And we'd like to do the series from 0 to infinity, but if we type in infinity, Desmos doesn't know how to write that infinite power series. So we have to have a finite upper limit here. That's why I'm using m. Taking more and more terms, watch how the power series starts to look more and more like the function 1 over 1 minus x, as long as we stay between -1 and +1. In fact, we can restrict this here. I can add in a squiggly bracket, -1 less than x less than 1, and that will only give us the portion of the curve for 1 over 1 minus x between x equals -1 and +1. So let's watch how this power series starts to look more and more like the function 1 over 1 minus x between x equals -1 and +1. As we take more terms, watch the convergence happen. We have this weird flip-flop thing back and forth, but even here, watch how the graph becomes more and more aligned with 1 over 1 minus x as we get closer to -1. Take more terms, and just for fun, let's take 1,000 terms here. Desmos might have some trouble handling that, but there we go. It actually did all right. And we can see how close we are here. This power series really only equals that function if we actually take an infinite series. So we'd have to go from 0 to infinity. And again, Desmos can't do that. But here we have a 1,000 degree polynomial, which is a really, really good approximation for this function 1 over 1 minus x. In the next section, we're going to look at starting off with a particular function, and we'll see how to create a power series based on that function, where the power series converges to the function. We'll start off with functions like e to the x, we'll start off with sine, cosine, and we'll see how to create infinite power series that converge to our function on some interval. As one final example in this section, look at problem 6. This will be really short. We want to find the center of this power series here. So let's start by writing the general form of the power series. The general form for a power series from the previous page is the sum from 0 to infinity of c sub n times x minus a raised to the n. For this particular power series, the c sub n is n divided by 2 to the n. So we could rewrite this a little bit if we wanted to. It's the sum, n goes from 0 to infinity, n divided by 2 to the n, that would be the c sub n, the coefficients, times x plus 2 to the n. Now we want to figure out what is the center. That's A. Well, I have x plus 2. The center is not 2. The center is, well, I have x minus a for the form. So I can think of this as x minus negative 2. The center here is a equals negative 2. That is the center for this particular power series.